This lecture will be dedicated primarily to an introduction to enzymes, what they are, a little bit about how they work, but principally to enzyme kinetics and interpretations of enzyme kinetics. We'll be saving a detailed discussion of reaction mechanisms for in-class discussions as well as a little bit next week. First of all, how do we classify chemistry of enzymes? Well, common nomenclature typically uses this sort of phenomenase type system where we say what the enzyme does and we tack an ASE on the end of it, and that's our enzyme name. So we have 6 classes according to this scheme developed by the Enzyme Commission. You can go to the website at the bottom of the screen if you want to look at the standard nomenclature for any particular enzyme you may be interested in. The interesting thing, though, is that we only see 6 different classes of enzymes. Oxidoreductases, which carry out redox chemistry, transferases, which carry out group transfer, hydrolases, which add water across a bond, lyases, which add or remove functional groups, isomerases, which carry out intramolecular group transfer, and ligases, which join substrates together, typically with the consumption of ATP as an energy source. Those numbers are important, right? We associate each of those numbers with a specific category, as we'll see. I don't want to spend a lot of time discussing each of these, but it's worthwhile pointing them out to you. So the oxidoreductases carry out oxidation reduction reactions. Typically, we'll call these dehydrogenases. That's a common name for this kind of enzyme, although not uniquely so. Here we're looking at lactate being converted to pyruvate with the concomitant reduction of NAD+. So this is our sink and source of electrons. The standard nomenclature for this L-lactate dehydrogenase is 11127. You can follow each of these numbers to lead you directly to exactly what the enzyme does. One is oxidoreductases. 1.1 indicates that our oxidoreductase acts on a CHOH donor. I'll point out to you that L-lactate has that functional group. And then 111 indicates that the acceptor is a particular molecule, in this case either NAD or NADP. And L-lactate dehydrogenase itself is the 27th enzyme on that list. So here we see that, again, oxidation of lactate to pyruvate, right? Notice what's happening to this hydroxyl here, and with, again, that concomitant reduction of NAD plus to NADH. I'm not going to go into the specifics of the mechanism here, but I'll just show you the business end of NAD plus. This is the nicotine section of that nicotine adenine dinucleotide, and we attack basically add this proton across this bond, and then we shift our electrons back to the carbon, ultimately back to the oxygen, and the proton is released. So there's where our proton comes from, but we formed a carbonyl here out of this carbon-oxygen pair, and then we've reduced this carbon at this point. Okay, so that's basically an oxidoreductase. I'm not going to give you a bunch of examples of these, but I wanted to give you the flavor of that, and we'll see much more in the way of enzyme mechanisms, and certainly this mechanism in particular, as the semester and year grinds on. So, transferases, group transfer reactions. Interestingly, we often require coenzymes, although we're not showing you any coenzyme in this case. This happens to be alanine transaminase. So here's alanine, and we are adding, where am I? Oops, oh man. In the transferases, we carry out group transfer reactions, movement of one functional group from one molecule to another, typically involving coenzymes, although in the case of transaminase, which I'm showing you here, that's not the case, I believe. What we're looking at here is alanine. There's its alpha amino group, and this is alpha ketoglutarate, right? Alpha keto glutarate. I'm hoping that you see what I'm referring to there. And then we take that amino group and transfer it to the alpha ketoglutarate, converting it to glutamate, right? And then with the result that the alanine is converted to pyruvate. As a little aside here, it should be interesting to you that we see that these group transfer reactions, right, we're going from alanine to glutamic acid, involves other intermediate molecules that are important in other metabolic pathways, alpha ketoglutarate and pyruvate being those two players. We'll see them elsewhere. Alanine transaminase 2.6.1.2. 2 means it's a transferase, of course. 2.6 means that it's transferring nitrogens. And 2.6.1 means that those nitrogens are amines, so it's a transaminase. And alanine transaminase is the second on the list. I'm not going to give you all of these for each of the examples, but what I'd like you to do, and I'll look for this in class on Monday and or Wednesday, is for you to follow through with the other enzymes on my list here. There are 4 more to go. I'd like you to assign them. So moving on from the transferases to the hydrolases, which are really transferases that just in which a water is accepting the transferred group. In the case of this example, inorganic diphosphatase, water is accepting paraphosphoryl groups. So we go from this pyrophosphate here, addition of water across that phosphoester, to form 2 inorganic phosphate molecules. The lyases, in which the substrate is lysed, right, or loosened, a bond is cleaved, and a double bond is frequently formed. So here is our example pyruvate decarboxylase. Reminder: go look up decarboxylase, pyruvate decarboxylase. So here we're converting pyruvate to acetaldehyde, and we form carbon dioxide. Isomerases. So this involves the structural rearrangement within a molecule, and this is just alanine racemase. I've not been careful about drawing the stereochemistry here for you, just illustrating that we're moving a nitrogen on this alpha amino group from one stereochemistry to another. And finally, the ligases, right? So here's another a little etymology from ligare, the Latin for bind. Synthetases are a group of these ligases, and they covalently link substrates using ATP, again, as an energy source. This is glutamate ammonia ligase, also known as glutamine synthetase. And you see here that we've got a couple of players going on here. Not only do we have, this should be a single methyl group here. Oh no, yeah, glutamate. This is glutamate, and then we have ATP and this amino group. So we're converting that from glutamic acid to glutamine, and there's the hydrolysis of ATP, resulting in the formation of ADP, release of inorganic phosphate. So those are our chemistries, and you might find it remarkable that any particular chemistry that you can find an enzyme performing will fall in one of those 6 categories. What about reaction kinetics? So kinetics, of course, comes from the Greek for move, and the basic metric or the basic tool for looking at reaction kinetics is measuring reaction rates. The reaction rate is our basic metric of the enzyme's activity. How quickly is it doing its job? That's the easiest way we can characterize the enzyme. And we use kinetic analyses for the quantification of perturbation effects. So we're perturbing the enzyme's activity either by manipulation of solvent conditions, of substrate concentration, with the presence of drugs, say inhibitor molecules, as well as by mutation. So I think it should be clear that all of these variations on a particular set of conditions, be it sequence conditions, be it substrate conditions or solvent conditions, are all going to change or alter, somehow affect the kinetics of the reaction. So we can quantify those effects and therefore quantify the significance or the meaning of any of these perturbations that we carry out. So kinetics is our main tool for understanding chemical reaction mechanisms of enzymes. So what are these enzyme mechanisms? And I told you that in this lecture we were really going to push off the details of enzyme mechanisms until a later lecture, but it's important at least to think about what enzymes are doing in general, maybe vague hand-wavy terms. And this does lead us into a discussion of kinetics. So I'll say the enzyme mechanism is transition state stabilization. So reaction rates are accelerated. That's what enzymes do. They accelerate reaction rates by lowering the activation energy barrier between the substrate and the product, which themselves have some intrinsic energy, some intrinsic delta G, or free energies, and then the delta G of the reaction is the difference between those energies. That will define the equilibrium conditions of the system, right? Which we favor, substrate or product, or reactant or product, if you will. But it's this transition state magnitude that determines how fast we move from one end of that equilibrium to the other. In an uncatalyzed reaction, we'll typically have a higher delta G double dagger than we will in the presence of the catalyst. So the enzyme in this case is acting as a catalyst by simply lowering, again, that transition state energy barrier. So I'm making an assertion here, the second point, and maybe it's a little overstated, but enzymes selectively bind neither substrate nor product, but the transition state. So again, that may be a little bit too forceful of a statement, but the point that I'm trying to get at is that a good enzyme is going to bind and stabilize the transition state perhaps to a greater extent than either substrate or product. And to the extent that we do stabilize the transition state, we accelerate the rate of the chemical reaction. So again, let me emphasize that an enzyme isn't going to change the relative proportions of substrate or product at equilibrium, right? Instead, what we're going to do is change the rate at which we move between those two states. You can imagine that a chemical reaction might never occur or occur very, very slowly in the absence of the enzyme, but the presence of the enzyme accelerates that dramatically. This is an example of just those kinds of rate enhancements. And here, how I'm defining enhancement, and you'll have to bear with me for a second until we define these rate constants, are the kcat, or the catalytic rate constant, divided by the rate constant for the uncatalyzed reaction. And we see that we get these incredible accelerations, right? 10 to the 17th faster in the presence of enzyme than in the absence of the enzyme. 17 orders of magnitude faster for this particular guy who's involved in nucleotide biosynthesis. Not really important what any of these are, but this is one metric of how good enzymes are at doing what they do. We'll talk about others as well. But the